Hello. Today we're going to introduce the course with an analysis of ages and time. We have to know geological time, and there are several ways to encounter time in our analysis of the history of life on the Earth. Now, when you look at places such as this here, you see layers of rock in the landscape. The layers tell us a story, much like the pages of a book. How do we understand these layers so that we can understand the story that is present within them? One thing that you will come to understand is that the layers here are each time increments, and that the tendency is that older layers, meaning time in the past, are superimposed on by younger layers on top, and so forth. So that in geology, there's a stacking of time. Today, the plan is to begin our general discussions of how we know the ages of rocks, and thereby of events in geological history. So this material is absolutely crucial to your understanding. So it's important to pay careful attention, even when we go into the details. Now, the relative ages of things is something that is not that difficult to understand. For instance, in our everyday lives, we're constantly evaluating the relative ages, say, of people. But in this course, we talk about the relative ages of events in the history of our planet. But let's just take people, objects, or events in our common understanding. Well, an elderly person is recognizable. And the person shown here is older than the person in the center, who is older than the young person over here on the right side. So the relative ages are that the person on the left here was born before the person in the middle, who was born before the person on the right. We don't know their absolute ages, but we know the relative ages. Young, older, oldest. Well, geology is a lot like a sandwich. I like to use this analogy because a sandwich, of course, begins with a slice of bread at the bottom. And a slice of bread, there first, can have ingredients stacked on top of it, which come later, covered again by another slice of bread on the top. Now, in general, in geology, we talk about this idea called geochronology, and that is time study of the Earth. So what came first? What comes next? And what is the most recent event? Now, geochronology, for the most part, to begin this segment, is the study of sediments. Because sediments are the debris made from broken rock or dissolved materials that accumulate with time. Now, the sediments accumulate as layers. We call these layers strata. Now, a single layer is called a stratum, and the study or description of layers is called stratigraphy. Now, all of this together, you can think of stratification and layering and so on as bedding. So you'll be hearing terms like these throughout our learning journey. Weathering leads to sediments, which are an accumulation of grains. We can tell the relative ages of things in sedimentary environments by what is placed on top of another. We will review the geological systems which were originally formulated to describe the sediments and sedimentary layers piled on top of one another. We will use this information to explore early estimates of Earth's age, which began with the study of layers of sediments and the fossils contained within them. After examining that, then we will find out how we get absolute ages, actual numbers, dates applied to the ages of the rock. So we can ask ourselves the question, how do we know what is older than what? Well, we start with simple observations and build from there. Gravity affects us all. It affects sediments too, and water that may hold the sediments. Gravity is pulling on every surface of the Earth towards the Earth's center. Now, over large areas, that leads to flattening of the water. Water always finds its level. Well, sediments added to that water will settle and sink and form a horizontal layer. Well, gravity acting on sediments and water will bring those sediments and water towards the surface to accumulate. And here we see that that accumulation is on the form of a new layer over an old surface. And over time, these layers build up and build up and build up until you reach a new surface all the way at the top that may be exposed to weathering, denudation, erosion, or further accumulation of sediments. Well, there are many things that can happen to these layers. They may remain as they are for very long periods of time in geologic history, or they could be altered, for instance, by a river channel cutting through them, like in this example. And that's a spectacular example, of course, because we can see it in many places, such as the Grand Canyon. Now, how do we put all of this together from first principles, starting with basic ideas? Well, one of the first people to do this was named Steno. Now, Steno, or Nicolaus Steno, he came up with 3 key observations that have since the 17th century allowed geologists to understand the relative timing of events in the geological record. Let's review some of these now. And we'll begin with our Grand Canyon example. Now, the Grand Canyon is, of course, an overwhelming sight. In person, when you're there, it's spectacular because of its scale. If you've never visited the Grand Canyon, I can tell you, you'll be surprised at just how big it is in reality. But looking out over the Grand Canyon, we see these horizontal layers that we've been talking about up to now. The other thing that's clear is that the river, the Colorado River, has cut down through this grandest of canyons. And on one side, as well as on the other side, there's a repeat in the sequence of layers. Now, for example, here we see at the top of the Grand Canyon light-colored layers of sandstone, which repeat themselves even many kilometers away on the other side of the Grand Canyon. Now, what does that tell us about the relative ages of things? Well, it seems that the layering was once continuous, connected across the canyon, which has since been carved down by the Colorado River, disconnecting these once connected layers. That is the first introduction to these three laws of relative age determinations handed down to us by Steno. The first is that as long as you have a system that's undisturbed, sediments added to that system by wind or water should find their level. So they accumulate as layers. Now, what's old or first is at the bottom. That gets covered by the younger material and so on. Now, that's called superposition because it's situated on top. Now, the next thing is that these layers, especially if they've been laid down in water of sediments, were originally horizontal. If you find that they are not horizontal in some layered rocks someplace that are obviously sediments, then change has occurred since they were formed. Now that idea is known as original horizontality. Almost all layers are horizontal when they formed, yet how could they be changed? Geological forces, erosion, and so on can do this. Finally, back to our Grand Canyon example, all of these layers were once connected to one another if you have the same rocks in the same sequence of layers. Now that's called original lateral continuity. All of this sounds pretty obvious, right? Well, that's easy for us to say, but now we have to remember that this is a profound idea, that we can read the record of the rocks by looking at the layers. The Grand Canyon is a good example to understand this further. What you see at the bottom here are what are known as stratigraphic sections. These are mapped, layered sections of the Grand Canyon in different places along the course of the Colorado River. These measurements expose different layers of different ages, but you can see laterally they can be linked to one another. And with this information, one can build, just by traveling down the canyon and mapping the layers on the side, a coherent story of the history of this part of the world, beginning with mudstones at the bottom, limestones above that, sandstones and limestones above that, and then limestone at the top. This is repeated throughout the Southwest United States. These different formations, here shown in this diagram, have been given names by geologists to identify their properties. Each of the formations is really a collection of layers that has a particular sequence of properties and fossil characteristics that identify that layer. The story that emerges when you analyze all of these layers is like a three-dimensional block map of the history of the rocks that compose the Grand Canyon. So it's spectacular because with these simple principles that I mentioned, you can read the rocks even in a place as huge and as complex as the Grand Canyon. So like a book, we have revealed to us the original shorelines of a story of ancient seas rising and falling in their sea level and depositing rocks at different ages with different histories of life under different climate conditions. So the beauty of the Grand Canyon, and really, literally any other place in the world with such stratigraphy, is that we can look at it and admire it for its grandeur, but see within it the history of the origins of different plant and animal species. Let's look at this in more detail, so we can use then general conclusions about the relative ages of rocks. Here, for example, is a road cut. Road cuts are very useful for geologists because they're areas where working crews have exposed fresh cross-sections of rock, where you have gravel on top of some rock, coherent rock, and then some plants, of course, growing on the top of that. Well, that cross-section leads us to sort of this general type diagram of which rocks came before what. Shown here on the left is some granite. The granite, you can see, which is in this pink stippled color, has blocks in the contact between the granite and what's above it in that yellow colored dotted pattern, which represents, say, sandstone. Well, the granite appears to have been weathered in its surface, and then the sand originally was deposited on top of that, found its level. Then the situation changed, and there's another rock that's on top of that in a bit of a darker color, and another rock on top of that in that sort of brick type pattern. Now, this sort of generic geological cross-section is very useful because we can use it to understand that the granite was there first, sand was deposited on top of it, mud was deposited on top of that, limestone deposited on top of that. And knowing under what environments these different rocks form give us more in-depth information of the history of this geological system. This is an example of what is older below and what is younger above. How about another example? Here's one where the bits and pieces of the sandstone here, shown in yellow, are actually incorporated into the granite. And then above the sandstone is shale, originally muds in the bottom of the ocean. And above that is limestone, kind of like reefs, coral reefs, that kind of thing. So that tells us about water depths. Coral reefs, relatively shallow, close to shore. Shale, mudstone, farther out into deeper water, and sandstone very close to shore where there's abundant sand. So looking at this, we also get an idea of water depth. Look at the granite though. The granite seems to have incorporated the sandstone. That's very different from what's in the left diagram, where the granite pieces are within the sandstone. How do we interpret that? Here, the granite is younger than what is above it, because the granite came later and incorporated the sandstone. Now that's a different idea from the one on the left, where the granite existed and donated pieces of itself to the sandstone. Here's an example. This is called a xenolith. Now in geology, we use lots of terms. This is a great one. It comes from the Greek words xeno, meaning foreign, and lithos, meaning rock. So this is a rock, and there's a little pen for scale there, that existed before the granite around it engulfed the rock and maybe carried it along for a little bit. A big step for our understanding of the relative ages of geological events by looking at the record of the rocks is something called the principle of components. We've looked at Steno's laws, which tell us about layers, that older layers tend to be covered with younger layers. Now let's look at the principle of components now, which is much like my analogy to the emulsion of salad dressing. Now, salad dressing has components in it. These are called ingredients. Those components comprise oil, vinegar, water, and spices. So those components, when left alone, unmix, which is why you have layer of oil at the top over the vinegar and water and spices at the bottom. And when we mix a salad dressing before pouring it on our salad, what we're doing is creating an emulsion so that these components are mixed together. And then when left on their own, they unmix. Well, we see this example all the time in the record of the rocks. Here's one. The principle of components can help us understand by looking at a picture such as this of an outcrop. Which came first? Well, how many components are in this picture? I count the dark blobs in the light gray material, which has different hues, and then some light-colored veins crisscrossing the outcrop. Now, it appears that the dark blobs came first because they're floating, essentially, in this light-colored rocky background. Those dark blobs look like they may have been connected to one another, but it certainly looks like a frozen example of an emulsion, like our salad dressing analogy. The blobs, though, and the gray material, in this case granite, that they're floating in, appear to be cut by younger veins. That's this light-colored stuff. So we can say that the different components in the picture, dark blobs, light-colored background rock, even lighter-colored cross-cutting veins, tell us that in that order, we have the order of relative ages. Oldest, dark blobs, a little bit younger, the light-colored granite material, and then everything is overprinted by these veins. That is how the principle of components gives us a story of which came first and what sequence of events just by looking at the details. Now, this introduces us in general to something in geology that is known as the rock cycle. Now, the rock cycle begins with molten rock that solidifies, and that molten rock then can be altered by remelting, by weathering, or by transformations by heat and pressure in a process called metamorphism. Crystallization of molten rock either is erupted like in a volcano or intruded into the crust yields the primary rock. We call this igneous rock. That igneous rock can be eroded from exposure to the surface, chemical changes by water, and so forth. That yields sediments, which are then deposited someplace and can also turn to rock, called sedimentary rock. Now, sedimentary rock and igneous rock can be affected by high temperatures, pressures, and chemical changes that are intrinsic to the crust, to the active style of our planet. And that's called metamorphic rock. Now, this is the basic outline of the rock cycle, which next time we will look at in even more detail. To summarize, looking at an outcrop and using the knowledge we have in hand, which of the different relationships here is best defined by age? Well, we can see layers at the top that are nice and horizontal. Remember the principle of original horizontality and lateral continuity? But there's a break right here where the rocks are different, just above where that person is standing. That break is a break in time. Any break in time like that in geology is called an unconformity because it does not conform to the sequence of events. There's lost time. So the best relationship here, as defined in this analysis, is this thing that's called an angular unconformity. So what are some questions that we can ask? The relative ages of things, which came before what, and therefore which event came before what event. With that knowledge, we can reconstruct the environmental history of rocks, and that's our beginning in the quest to read the record of the history of our planet in the geology.